Hello, good evening everyone. So we'll start the class now. So welcome to the problem solving session for the NPTEL online course regarding wastewater treatment and recycling. I am Akash Shah and I am one of the teaching assistant for this course. I am currently a PMRF scholar at the Department of Civil Engineering in IIT Madras, where I am pursuing my PhD in environmental engineering. So we will briefly see whatever we discussed in this week's course. So we are into week 6 now. So we started with the introduction of biological treatment of wastewater, where we discussed about various type of microorganisms, the basics regarding the biological processes, its metabolism, respiration, and the principles. And then we moved on to learning about the microbial growth and its kinetics, the requirements for the microorganisms, and about the microbial growth phase in batch mode and in continuous mode. Also, then we moved onto the monod kinetics for microbial growth. And then we learned about the activated sludge process, where we discussed all the biochemical reactions, the process modeling, oxygen requirement, and the design criteria. And then we discussed briefly about the trickling filter and the rotating biological contactor. So I have some subjective and objective type of questions regarding these topics. So do you want me to go through the activated search process again with the process modeling derivation, or do you want to directly go into the subjective questions? Please let me know. Because process modeling of this activated sludge process is a major part in this biological treatment. So if you want to have a refresher regarding that, or okay, what about Saket? Is it fine for you? Okay, so we will briefly discuss about the derivation of activated sludge process uh, regarding the all the biological parameters. So please have your pen and paper with you. I will start the derivation. I hope my screen is visible. Okay, so suppose in any biological process, we have two main reactors. Where first reactor where we do the aeration part, where basically the biological process happens, and in the next reactor we have the settling of the biological biomass. Okay, so in the aeration, in the first reactor we do perform the aeration. So suppose the influent flow is Q naught, and we have the substrates as the BOD, which is S naught, and the biomass concentration as X naught. So these are my input parameters. And regarding the aeration chamber, suppose the volume is V, the substrate concentration will be S, and the biomass will be X. So we measure biomass in terms of ml VSS, that is mixed liquor volatile suspended solids. Okay, so as we know, in any continuous reactor with aeration, so whatever the final effluent concentration will be there, will be carried forward to the settling chamber. So, so both the substrate concentration and the biomass concentration will be same, which will be going into the settling chamber. But here the inflow will increase, which will be equal to my initial Q naught plus the sludge recycling, which is coming from the settling. We will see from where it is coming. So after the settling, a part of it will be wasted. So that will be my QW, where again the substrate concentration will still be the same, because there is no biological, we assume that there is no biological process happening in the settling chamber. So the substrate concentration will be same, it will be S. But the residual biomass concentration will be XR. And some part of inflow will be coming out as the outflow as effluent. So the flow will be Q naught minus QW. So whatever has been wasted, we will subtract it from the initial Q naught. So it will be Q naught minus QW, the substrate concentration remaining as S, and the effluent biomass concentration as XE. and a part of it will be recycled back to the aeration chamber. Okay, so it will be QR, again substrate concentration remaining S, and the biomass, residual biomass concentration as XR. Okay, so this was the flowchart of the activated sludge process. Are you comfortable with it? Is there anything which do you want me to explain again? Guys, please respond. Okay. Okay, so last time we learned about developing the mass balance equations for each of the contaminant. So here we will see how to do the mass balance for first the biomass and then the substrate. Okay, so first I will write the steady state mass balance for biomass. So first will be my influent biomass plus whatever biomass has been produced in the system. In the system means I am talking about the aeration chamber, which will be equal to my effluent biomass plus whatever has been wasted biomass. Okay, so what will be my influent biomass? We know that influent biomass concentration is X naught. So to keep the units constant throughout this mass balance equation, we will multiply it with the Q naught. So it will be, we know Q is meter cube per day into X naught will be milligram per liter or meter cube. So everything will be in terms of milligram per day. Okay, so each of my term in this mass balance will be milligram per day or kg per day, anything that is weight per time. So I will erase this. So the unit should be constant throughout the mass balance. Now we have to write whatever the biomass is produced. So suppose, yeah, Saket, you want to ask anything?
Sir, what is the meaning of biomass produced?
Yeah, biomass produced means there will be we will be aerating the chamber, right? So when we are aerating the chamber, so whatever the biomass that is formed by new cell synthesis is our biomass produced. Okay, so suppose with respect to time, my production is dx by dt. This is my biomass produced per time. But now, if you see the unit of this, the unit of this will be milligram per liter into time. But we want with respect to milligram per time. So we have to multiply with some volume term or some liter term. So that liter will cancel and it will be mg per time. So we will multiply here with the volume of the reactor. So my total biomass that is produced in the system will be V into dx by dt. That is my total biomass per time. Okay. So it is because of aeration. We are providing nutrients, oxygen to the whatever biomass present there. So it will form new cells. Okay. Through the process of anabolism, it will form new cells. And with the help of catabolism, it will degrade the substrate. So we have learned about two major biochemical reactions that is going on. One is anabolism and one is catabolism. So anabolism will be helping us to produce new biomass. So this was my left hand side. So what will be my effluent biomass? We know that the biomass coming out from the system is Xc. So we will multiply with the corresponding flow rate, that is Q naught minus QW, what we have seen here. Okay, so it will be Q naught minus QW plus whatever is wasted, it will be QW into XR. So is it clear? The mass balance equation for this biomass. Saket, is it clear now? Okay. So now we will see at steady state what will be my mass balance of the substrate. Okay, so for the substrate we will similarly write, but instead of biomass we will see how my substrate is changing. So it will be q naught into s naught. Now here in my previous equation the biomass was produced, so it was plus dx by dt, but here my substrate is being consumed, so it will be minus ds by dt. Again we will multiply with the volume term, so it will be v ds by dt. Okay, and it will be equal to my q naught minus qw into s plus qw into s. So similarly, we will write the mass balance for the substrate also. So the only difference is for the case of biomass, it is being produced. So we wrote plus dx by dt. But in the case of substrate, it is being consumed to produce the new biomass. So it is minus ds by dt. Similarly, for now, we will write the mass balance or we will write the equation for biomass growth. So we have introduced a term dx by dt. So we will see what is dx by dt. So biomass growth is being assumed to be happening in first order. So it will be directly proportional to x, right? dx by dt will be directly proportional to x. So if I want to include the equal sign, I will put a constant of proportionality. So it will be equal to kx. But in the case of biomass, we write it as mu x. So mu is the growth rate. So dx by dt will be equal to mu x. But also, if we have learned about the growth phase of the microorganism. So after a point of time, there will be some decay of the microorganism during the endogenous phase. So some part of microorganisms will be decaying or rather dying. So the net biomass that is being produced in the time will be mu x minus the decay constant into x. Okay, so my net biomass growth will be dx by dt is equal to mu x minus the decay constant into x. Again, we learned about monod kinetics. So in monod kinetics, mu is written as mu max into s by ks plus s. So here mu max is the maximum growth rate. S is the substrate concentration. Ks is the half saturation constant. So what is half saturation constant? I will briefly explain. So if you see the monod kinetics graph, it is something like this. So after a specific time, it is reaching saturation. So the graph is plotted with respect to mu and x, or rather we can say, yeah, mu with respect to s, the substrate concentration. So as my substrate concentration is increasing, it will reach a saturation growth rate, that is my mu max. So suppose we are considering the growth rate which is half of my maximum growth rate, that is mu max by 2. So whatever will be my substrate concentration during my this half rate, that will be equal to Ks. That is my half saturation constant. So whenever my substrate concentration will be equal to the corresponding concentration when my growth rate is half of the maximum point. So that will be my saturation, half saturation constant, that is Ks. So we will put this all in the equation. So it will become mu max S into X divided by Ks plus S and then minus Kdx. Okay. Is there any problem with this? Please let me know. I will explain. And at last, we will write about the substrate utilization, which is my ds by dt. Or rather, I should write minus ds by dt because substrate is getting consumed. So I will write it as 1 by y dx by dt. So here I am trying to write everything in terms of my biomass. So what is this Y term? Can someone tell me? What do you mean by Y? Anyone? You can type it in the chat box. Hello. So Y is my yield coefficient. That is the amount of biomass produced per gram of substrate. So I have written in terms of Y. That is my yield concentration. So it will be equal to again 1 by Y dx by dt, as we have seen previously, will be mu max S Ks plus S into X. Is it okay? Till now everything is clear? Any clarifications required? Guys, please respond something. Others? Shrina, Sunanda and Aditya, are you able to catch up? Okay. Okay, so we'll now come back to our first equation, that is my mass balance of the biomass. Okay, so in any activated sludge process, we assume that the influent biomass concentration and the effluent biomass concentration both are zero. So if both become zero, suppose this is my first reaction, so what will happen to my reaction 1? It will become, the first part will become 0 in the LHS, and also the first part of the RHS both will become 0. So it will simply become V dx by dt is equal to QW into XI, right? Okay, so again we will substitute my dx by dt because we have previously found out what is dx by dt. So it will be V into mu max S by Ks plus S into X minus KdX is equal to my QW into XI. So my mu max S by Ks plus S will be equal to QW XR by Vx plus Kd. I am just rearranging the terms. So this is my equation 2. Suppose this is my equation 2. Okay. Now moving on. So how else can we define my dx by dt? So again, the net growth of biomass.
Sir,
Yes.
uh, if we did not assume x naught is equal to xe,
No, it is
then what
not.
happened?
It is not x naught is equal to xc. It is both x naught and xc are zero. We are not assuming that my input and output biomass concentration is same. We are assuming that both are zero because we assume that whatever biomass we have in the system is being utilized for the degradation. We are not assuming that the wastewater that is coming into the system is carrying any biomass. Okay. So once we have stabilized the system, it means that whatever raw wastewater that is coming into the system, it doesn't have any biomass. So all the biomass already present in my aeration chamber are utilized for the production of new biomass. And similarly, we are also expecting that in the effluent, there is no biomass. So that's why Xe term is also becoming zero. I'm expecting that all my biomass will be settling down. It will either come as a recycle or it will be wasted. Okay, so these are the two major primary assumptions in the activated sludge process. Is it clear, Saket?
Sir, yes, sir.
Okay. So we can write dx by dt also in terms of q, x and v. Okay, so it will be qw into xr by v. So if we see the unit of this, q is meter cube per day into xr milligram per meter cube divided by meter cube. So it will get cancelled. So again dx by dt we will be getting in terms of milligram per meter cube per day, which is equal to my unit of dx by dt. So like that also we can write. And if suppose I am dividing both side by x, so it will become dx by dt into 1 by x will be equal to qw xr by vx. Okay. Also we know that my dx by dt can be written in terms of what? It can also be written in terms of my yield or my specific substrate utilization ratio minus the kdx. So either I can write dx by dt in terms of mu x minus kdx, or I can write in terms of my specific substrate utilization. So it will be minus rsu minus kdx. Okay, so here, so so here also I will divide by x. So it will become 1 by x dx by dt minus rsu y into rsu minus x minus kd. And then I will substitute this equation here. So it will be qw xr by vx my is equal to my y rsu by x minus kd. Okay. So now this term is also denoted as 1 by theta c. So again we are introducing a new term, that is theta c, that is my mean cell residence time. So theta c denotes that how much time my biomass is being present in the system. So my theta c is equal to Vx by Qw into Xr. Okay, this is how I define my theta c. So this term gives the indication for how much time or for how much days my biomass is being present in the system. So this is denoted as 1 by theta c, which will be equal to my y rsu by x minus kd. Okay, and what is my rsu? Is my specific substrate utilization rate, which is also known as, which can also be defined as q naught into s by s minus s naught minus s by v. And q by v, again I can write it as my HRT or theta. So this is my HRT, which is the hydraulic retention time. So if I combine both these equations, so both this equation A and B, if I combine, I will get my 1 by theta c is equal to y s naught minus s theta x minus kd. And here finally we can write v q theta cy into s naught minus s by x into 1 plus kd by theta c. So this is the main equation which we have to remember to find out any of the parameters. Suppose you are given all these parameters, you have to find the volume of the aeration chamber. We can find out with the help of this equation, or vice versa for any other uh, parameters that we want to know. So we will solve some problems. We will see how to make use of this mass balance equation and all this equation to find out the different parameters related to my activated sludge process. So do you have any doubts regarding any of the concept till now? Okay, so we will now see some of the problems. Okay, so this is the first problem. So the first problem says an aeration basin receives 3,800 meter cube per day primary settled wastewater. The influent and the effluent soluble BOD, which is my substrate, S naught and SE. It is my it is 150 and 6 milligram per liter respectively. The process related data are yield is zero point 0.5, decay rate KD is 0.06 per day, theta C, which is my mean cell residence time as 10 days, and my BOD5 to ultimate BOD ratio is 0.68. So you have to calculate the biomass growth and the oxygen utilization. So please note down the uh, information given in the question. We will try to solve this question now. Is there any problem understanding the question? I hope not. So remember here the yield that is given is yield total yield, right? So we have to find out what is my observed yield, because as I told you there is a net growth of biomass. Some biomass is being produced and then some are getting decayed. So there is a net growth. So there will be also a net yield. So we will see how to find out the net yield or observed yield in this case. Okay. Okay. So we will,
Sir,
yeah,
sir, BODL means?
BODL. No, it is BOD. Okay, sorry. It is the ultimate BOD. Okay,
Yeah,
BOD
yeah.
ultimate. Okay. Okay, so we will see how to solve this problem. So this is my first question. My flow rate is 3,800 meter cube per day. My S naught value is 150. My SE value is 6. My Y is zero point 0.5. KD is 0.0. What is this KD? KD is 0.06. Theta C is 10 days. And my ratio is 0.68. Ratio means BOD5 by ultimate BOD. This is zero point 0.6. Okay. So as I told you, we have to first find the whatever is my observed yield. So my observed yield will be equal to Y divided by 1 plus KD theta C. So this is my equation for my observed yield. So my observed yield will be 0.5, 1 plus 0.06 into 10. So it will be equal to 0.31 gram VSS per gram of BOD5, right? So this is my observed yield. So once we know the observed yield, we will try to find out what is my biomass growth. Okay, so my biomass growth, suppose I am denoting it with P, will be observed yield into, or don't want to confuse with X, observed yield into the flow rate into S naught minus SE. Okay, so observed yield will be 0.31 into 3,800, 150 minus 60 into, to change it into kg, I am dividing it by 1000. So it will be equal to 170 kg VSS per day. Is there any problem understanding this?
Sir, why we write here VSS?
VSS. See, biomass is always in terms of VSS, right? Whenever we define biomass, it is mostly or rather always in terms of volatile suspended solids. Okay, so always. you can write kg microbes, right? You have to write 170 kg microbe per day. But instead of writing microbes, we write it as in terms of VSs. That is my volatile, because we measured in terms of, we have learned different types of solids, right? So my volatile suspended solids is always being equated to my biomass. Okay, so that's why we write in terms of VSs. So this was my biomass growth. So now, so what will be my O2 utilization rate? It will be simply Q naught, Q into S minus S naught minus S by the ratio F minus 1.42 into P. So why this minus 1.42 into P? Can someone tell me? It is the oxygen requirement per gram of biomass. So that's why we are subtracting it from my oxygen utilization. So the total oxygen utilization will be the total oxygen required for the system minus whatever oxygen is being utilized by the biomass. Okay, so it would be 3800, 150 minus 6 divided by 0.68 minus 1.42 into 170. So it will simply become 805 minus 241. Here again we have to divide it by 1000. So it will be 564 kg of oxygen per day. Is it clear? So first we found out like what is my observed yield. With the help of the observed yield, I found out what is my biomass growth, and then with the help of this, I found out what is my oxygen utilization. So I hope you have noted down. We'll move on to the next question. So these were my answers: 170 kg VSS per day and 564 kg O2 per day. Okay, so first questions I have solved. So now move on to the next question. So it says a completely mixed activated sludge process is to be used to treat wastewater flow of 5 mld, okay, of ultimate BOD of 300 milligram per liter. And then all the MLSS value, SC, recycle ratio, total yield, K, everything, decay constant, everything is being given. All the design parameters are given. So we have to find out the aeration tank volume, the operating BSRT. BSRT is my, uh, or you can say mean cell residence time. MCRT or BSRT both are same. And then hydraulic retention time. So effectively you have to calculate V, theta C and theta. So here we will see one more concept. Okay. I hope you have written or taken a screenshot of this question. So we will see what concept we have to see here. So my question 2. So before starting this question, we know that my ds by dt is equal to Umax S by Ks plus S, right? And this mu max, I know I can write K into X. Okay, mu max I can write K into X divided by Ks plus S. Now suppose we have a condition where my Ks is very much greater than S, or I can say there is a limited substrate. My substrate is very much limited. Okay, so what will happen to this term, this particular term? In this particular term, this will be approximated to 0 in with respect to Ks. So my ds by dt will simply become k into x into s divided by ks, right? So here k is also a constant, ks is also a constant, small k into capital small k by ks. So I will substitute this as capital K, k by ks. So I will substitute, and this is my specific substrate utilization rate constant, and the unit will be equal to volume per mass per time. Okay, so here my ds by dt will become capital K x s. So what will be my substrate utilization rate? My substrate utilization rate will be ds by dt by x. So it will be k capital K s x by x. So it will be my k capital K into s. So my substrate utilization rate in case of limited substrate concentration, okay, it will be k into s. And also we know that my ds by dt can also be written in terms of q naught s and v. So again, if I divide this term by x, it will become my RSU, and it will be equal to q into s naught minus se by x va, va or whatever my volume of the reactor v. Is it okay? Any problem with understanding this concept? This is in the case of limited substrate. So mostly in case of ASP, we will consider it to be in the uh, condition of limited substrate. Okay. So in this question, particularly why I derived this? Because if you see the question here, the K term is given in terms of 0.1 liter per milligram per day. So by seeing the unit, you have to know that what condition we have to take, or how we have to go, like which procedure we have to go through to solve the problem. Because here k was not given in terms of per day or per hour, it was given as liter per milligram per time. So we can see whenever this type of k is required, so we have to write everything in terms of RSU. Then only we will be able to utilize this. Okay. So, okay. So in my question, it is given as Q is equal to 5 mld, S naught is equal to 300, X was 2000, effluent is 10, my YT is zero point 0.5, capital K value is zero point 0.1, KD value is zero point 0.1, and also it is given ml_VSS is equal to zero point 0.8 of ml_SS. Okay, so we will see how to solve this problem. So first we will calculate RSU. So RSU is KS or SE, whatever we can write, KS or KSE. So it will be zero point 0.1 into 10, 1 per day. This is my RSU. Again, we know RAC is equal to Q S naught minus SE by X into V. So it will be becoming 1 is equal to 5 into 10 to the power 3, because it is given in terms of million liters per day, into 300 minus 10 divided by my biomass concentration 2000 into V. So from here we can find the volume. So my volume of the reactor will be, can someone calculate and tell me what is the volume of the reactor? Please tell me the volume of the reactor. Is anyone solving?
725.
725. Okay, right. 725. Okay, so the next part we have to find the mean cell residence time. That is my theta c. So we have just derived that theta c is equal to my yt ksc minus kd. So simply we will put all the values. So my yt value, what is my yt value, is 0.5 into zero point 0.1 into 10 minus zero point 0.1. So this is 1 by theta c. So this will imply my theta c will be, my theta c will come as 2.5 days. Okay. So is it clear? Pretty simple question. So this is how we have to do the problem. Okay, so we'll move on to the next question. So again, this question looks very big, but each of the part is a one line answer. So we have 6 parts here. So again, an activated stress question where all the kinetic constants are given, y, kd, k and ks. So here if we see, the k value which is being given is per day. Okay, so here we don't have to bring into the concept of specific substrate utilization rate. So everything is given in per day. So whatever we have derived before, we can directly take those formula and try to find out the answer. So whatever we have learned previously, we can directly substitute the values there. So only you have to be careful when the constant is given in some other units, we have to fine tune our equations. So here we have to calculate what will be my effluent soluble BOD, that is my SE, what is my removal efficiency, what is the concentration of microorganism, that is X, my MLSS value, then the specific BOD utilization rate, and then food to microorganism ratio.
Here, what is value of Ks?
KS. KS is 50 milligram BOD per day, per liter, sorry. Okay, Ks is 50. We have 4 parameters, Y, Kd, K and Ks. So that those are zero point 0.5, 0.05, 5 and 50. Okay. Okay, so we will see how to solve this problem. So first we have to find out the effluent BOD. That is my SE. So what will be my SE? Simple direct formula. it is Ks 1 plus Kd theta c divided by theta c y into K minus Kd minus 1. Simply, we have derived this. So it will be 51 plus 0.05 into 5 divided by 5 into zero point 0.5 into 5 minus 0.05 minus 1. So it will come as 5.6 and the unit will be milligram BOD5 per liter. So it will be 5.6. So my effluent, so we found out that my influent concentration was 300 or rather 200, sorry. My influent is 200 and my effluent is 5.6. So my efficiency, what will be my efficiency? Efficiency will become S naught minus SE divided by S naught into 100. So it will be 200 minus 5.6 divided by 200 into 100. So it will be 97.2%. Okay, pretty simple. And then again, we have to find the biomass X. We will directly, whatever uh, formula we have derived before, X is equal to Y into theta C, S naught minus S by 1 plus KD theta C into theta. Theta is the HRT. So we have every data. It will be zero point 0.5 into 5, 200 minus 5.6. Okay, I will change into hours per day, 24 hours per day, divided by 1 plus 0.05 into 5 into theta is 6 hours. So my X value will be 1555 milligram VSS per liter. So this is my biomass concentration. So if I know my biomass concentration, can someone tell me what is the MLSS value now? So I have told you several times that biomass is written in terms of MLVSS. So what will be my MLSS? Tell me. Will it be more than my VSS or less than my VSS?
It is total suspended solids.
Yeah, it is total. So it will be more than. So what will be my MLSS? The ratio is 0.78. VSS to TSS ratio is 0.78. So what will be my MLSS? It will be simply MLVSS by my ratio. So it is 1,555 divided by 0.78. That is 1994 mg TSS per liter. Okay. Then the substrate utilization rate RSU will be equal to S naught minus S by theta x. Or you can also write it as S naught minus S Q by Vx. But here Q by V is equal to theta. Right? So I am writing theta x. So it will be 200 minus 5.6 divided by 6 hours into 1,555. So it will be zero point 0.5 mg BOD5 per mg VSS. Okay. So this is my substrate utilization rate. And finally, I will find the F by M ratio. So F by M ratio also direct formula Q naught by theta x. S naught by theta x. So it will be mg per liter into 24-hour per day divided by 6 hour into 1,555. So my F by M ratio is 0.51 mg BOD5 per mg VSS day. Right, so we have found out all the parameters that are required in the question. Is it okay? I am working out each and every problem. I hope it is clear to you all. Okay. So this is another problem. This problem is related to the monod kinetics. So we have a reaction, or rather an equation related to monod kinetics. So please take a screenshot of this problem. Try to solve it. I will tell the answer in the next class. Or if you have solved it before, you can send it to me by mail. Okay, it's a very simple problem, but you have to be careful. So please take a screenshot of this problem. We will discuss in the next class. Or whoever is interested, they can send me the answer. I will help them to solve. Okay. Okay. So we'll try to solve the multiple choice questions now. So please respond in this part. I hope the subjective numerical type questions were useful for your understanding. So the first question says, during secondary treatment of wastewater, the influent of primary clarifier enters the. So during the secondary treatment, from the primary clarifier, what is the next unit? So the options are aeration tank, secondary clarifier, disinfection tank, none of the above. So what is the right answer? So secondary treatment means my biological treatment. So what is the
Aeration
first?
tank.
Aeration tank, yes. So this is the right answer, aeration tank. Because after my primary settling, we will move into the biological treatment. So the first process of biological treatment is the aeration. So where the microbes will grow and it will degrade the whatever substrate as BOD present in the system.
Sir, it may also be disinfection tank if we di- discuss about
No, why? How it can be
primary
disinfection tank?
treatment.
Sorry,
In case of primary treatment of wastewater.
primary treatment of wastewater. So you are doing only just the primary treatment and directly disinfecting. You don't want to remove the organic solids or organic dissolved solids present in the wastewater. If you don't want to remove them, then you can directly send it to the disinfection. Okay. But our major problem is the organics present in the system, or rather the dissolved organics, which cannot be separated through any filtration or any physicochemical methods. So for that we require the biological treatment. And okay, so first the primary treatment, biological treatment, if required tertiary treatment, then disinfection. So this is how it goes. Okay, so next question. A probable electron acceptor in anaerobic anoxic respiration is organic matter, nitrate, sulfate, all of the above. So which of these is an electron acceptor? Others, please try to answer. You can write it in the chat box. Do you know what is the electron acceptor in case of aerobic system? No answer. So for aerobic system, it is oxygen. The final electron acceptor is the oxygen in aerobic system. But in case of anaerobic or anoxic respiration, what is the electron acceptor? Guys, are you going through the
Or-
lectures?
Organic matter?
So it is all of the above. So in the case of anaerobic system, it is organic matter, but in the case of anoxic system, we have we have both the sulfate and the nitrate. Okay, so I have asked about anaerobic, anoxic, so all the above is the correct answer. Okay, so the next question. Advantage of biological treatment process over physico-chemical process are A. Cost effectiveness, B. Lower energy requirement, C. Both A and B, D. Less time consuming. What are the advantages of biological system or biological treatment process?
A and B?
A and B. So C is the correct answer. That it is both cost effective and lower energy intensive. Okay, but typically, in a biological treatment process, it will take more time to degrade the organics or the contaminants. So it is more time consuming, not less time consuming. Okay, next question. When an organic material is used as an energy source, it is converted into stable end products by the process of. So while discussing ASP, I introduced two of the terms. So I already discussed it. Please tell me what is the answer. So organic matter with the help of energy is converted into stable products. So that means it is being decomposed or degraded. So that process is known as anabolism, catabolism, catalysis, pyrolysis. What is the answer? No one knows. Shall we see the answer? The answer is catabolism. So whenever an organic matter is degraded into stable products, what are the stable products? It will be carbon dioxide, water, or any other gases, any other greenhouse gases. So it is called as catabolism. And anabolism means the bacteria are using energy to form new cells. That is anabolism. Okay. Next question.
And the,
Endogenous. Yes.
what,
Yes. Tell me.
and the, what is metabolism?
Metabolism.
Anabolism and metabolism are similar.
No. 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 It both constitute metabolism. Okay.
It's both means both are
Ha.
same.
No. Both constitute metabolism. Metabolism is the overall reaction that is going on in the microbe. Okay. So what is endogenous respiration? A. Derivation of energy required for cell synthesis. B. Derivation of energy through oxidation of own protoplasm of the microorganisms. C. Derivation of energy for synthesis from inorganic substances or from photosynthesis of microorganisms. D. All the above. So here we are talking about endogenous phase. So in endogenous phase, there is a decay of microorganisms. So which of the statement defines endogenous respiration? So endogenous phase means decay of microorganisms. See, both options A are, and C are talking about synthesis. Synthesis means formation of new cells. Okay, so it is not talking about decay of microorganisms. It is talking about synthesis of microorganisms. So both option A and C are incorrect. D will also be incorrect. So it is option B. So it is the derivation of energy from the oxidation of the protoplasm of the microorganisms, and thus it is getting decayed. So it is known as endogenous respiration. Okay. So in the absence of any suitable external substrate, the microorganisms derive their energy through the oxidation of their own protoplasm, and hence they get decayed, and this is known as endogenous respiration or decay. Okay, next question. Identify the most appropriate choice for statement A and B. So statement A says the nutrient requirement is lower in anaerobic process than aerobic process. B, the growth rate of microorganisms is lower in anaerobic process. So are both the statements true? Both are false. A is true, B is false, or B is true, A is false. So the first question, so it talks about aerobic and anaerobic processes. It is talking about the nutrient requirement and the growth rate. So you have to compare anaerobic and aerobic processes in terms of nutrients and its growth rate. So in which of the process my growth rate will be high, anaerobic or aerobic?
Aerobic.
Aerobic, right? So if my growth rate is high, so my nutrient requirement will also be high. Okay, so both statements are true, right? Now, the next question. The sludge volume index of wastewater refers to the duration of solid retention, total organic content, sludge volume produced during secondary treatment, or settling characteristics of the sludge. So, which of the following statements refers to the SVI or the sludge volume index?
Settling characteristics.
Settling characteristics, yes. So, it defines the settling characteristics. Now, next question. Identify the correct statement regarding ASV. So it says F by M ratio of extended aeration is higher than conventional ASP. F by M ratio of extended ASP is lower than conventional ASP. HRT of extended aeration is lower than conventional ASP. SRT, solid retention time of conventional ASP is greater than extended ASP. So here we are talking about conventional ASP and the extended aeration ASP. So which of the following option is true? We have seen various modifications in ASP. So here we are comparing extended aeration and conventional ASP. So extended aeration means we are providing the aeration for a very long extended duration, right? So if we are providing aeration for a long time, that means my HRT will definitely be higher. So option C is incorrect. Now solid retention time. So if I am giving more and more aeration for extended periods of time, my solids will be retained for more time. So again, it will be greater in case of extended aeration. So option D is also incorrect. And then my F by M ratio. My F by M ratio, since I am providing longer duration of aeration, the microbial will slowly grow from log phase to stationary phase to endogenous phase. So all the food will be consumed and the microorganisms will increase. So my F by M ratio will be lower in the case of extended aeration. So option B is correct. Okay, did you understand? So we have to compare F by M ratio, HRT and SRT. My HRT will be higher, solid retention time will be also higher, but since for longer period of time we have extended this process, so my food will be getting consumed and my microorganisms will increase, so my F by M ratio will be less. So option B is correct. Now next, the degradation of organic matter in biological treatment process is typically due to photoautotrophs, photoheterotrophs, chemoautotrophs, chemoheterotrophs. So we have four different types of microorganisms. Photo means they derive their energy from light. Chemo means they derive their energy from chemical reactions or chemical energy. Auto means they depend upon inorganic sources. Hetero means they depend upon organic sources. So in any biological treatment, what do you think typically happens? What type of degradation pathway happens? So it is basically through chemical energy and organic sources, right? So chemoheterotrophs will be governing the biological treatment process. Okay, next question. The rate of microbial growth and metabolism depends on. So here it is talking about microbial growth and metabolism. So it depends on F by M ratio, solids retention time, sludge volume index, none of the above. What is the right answer? It is pretty simple. This is the last MCQ I'm having. So please try to answer this. The rate of microbial growth and metabolism will depend on. So for microbial growth, it requires food, right? It requires the substrate. So definitely it will be governed by my food to microorganism ratio. Okay. So food to microorganism ratio is the correct answer. Okay, guys. So these are all the questions that I had for today, for today's session. So kindly look back through all the questions that we discussed today, all the numerical type and also the objective types. You will get this recording and also this PPT available. So if you have any doubts now, you can answer. You can ask me or we can close the session. You have any queries regarding any of the topics or anything that you want me to discuss? Maybe I will discuss in the next class or something. Please let me know.
Sir, can you share some numerical problems related to this topic and previous topics?
This topic means ASP. I have discussed four, five problems, right? So
Yes, sir.
what else do you require? You can refer any standard book for most questions or any previous year gate questions, because the more or less type will be same. Whatever I have discussed, I have tried to cover all the different types of questions. So conceptually, if you have any problem, please let me know. Questions you will get.
Sir, only sir numerical problems.
Then you have to refer to previous year gate problems of this topic or refer to any standard book. Like last time told you that Metcalfe and Eddy or PV and Rowe. So you can refer to these books for more problems. Okay, I will see if I have any more questions. I will send it to you over mail. Okay.
Yes, sir. Thank you.
Okay. Abdul and Ravindra, do you have any doubts?
Yes. Okay, sir.
Okay. So we are done with today's session. If you have any doubts or any clarification, please let me know. Or you can leave the session.
Sir, can you explain rotating biological contactor?
Rotating biological contactor, right? Okay. Just a minute. So I will just briefly discuss like what is a rotating biological reactor. So in this we have a shaft, okay, and on this shaft there are some circular plates type mechanism is being fixed. So this is the side view. This is my shaft, and these are all my circular plates. So the front view will be like this. Okay, this is my shaft. So it will be partially submerged in a wastewater. Okay, so this circular plate will act as a medium of growth for the microorganisms. Okay, so we know that in case of ASP, it's a suspended growth system. But in the case of RBC, it's an attached growth system. So this plate serve as a media for the growth of microorganisms. So suppose this wastewater is flowing in this direction. So when the wastewater is coming here and getting in contact, and this disk is continuously moving. This disk is continuously moving. Okay. So suppose my wastewater is coming, it is getting in contact with this media. So in this disk, there will be growth of microorganisms. There will be growth of microorganisms. Okay. So now when the organic matter present in the system, suppose these are all the organic matter, it is coming and getting attached to the media, and there is microorganisms also present, and while this disk is rotating, it will come in contact with the atmosphere, or rather oxygen. It will come in contact with the oxygen. So the microorganisms will use the oxygen present in the atmosphere, and whatever the organics that is coming into the wastewater will be getting degraded with the action of the microorganisms. Okay, so this shaft will be moving, and slowly there will be a biofilm growth. There will be a biomass growth on this disc or this plate. So the thickness will slowly increase. Suppose this is my plate, this is my plate. So the biomass growth will slowly increase, and at a point it will increase so much that the inside of this biomass film will not get access to oxygen. So oxygen is coming from here. So the inside part of this biomass film will not get oxygen. So once it is not getting oxygen, it will go to endogenous phase. It will decay. So when it will decay, the entire biomass will slug off from the system, and then it will move into the secondary clarifier where the total biomass will be settled. So in this way, my organics will be getting degraded, and also my biomass will be getting removed from the system. Did you understand? This is an attached growth system. So in the case of ASP, in my aeration type, the all my microorganisms were suspended motion, in a suspended motion. So they were moving here and there with the help of this stirrers and coming in contact with the organics. But in the case of rotatory biological contactor, it is continuously moving. So the organics are coming in contact with the shaft and then it is moving in a circular motion. So when it is moving in a circular motion, it is getting in contact with the oxygen. So with the help of oxygen, the microorganisms are degrading it. So like that, many shafts are there parallelly and there are also many discs. So in this way, you can increase your efficiency, right? Is it okay?
Yes, sir. Got it.
Okay. So if your doubts are clear, please you can leave the session.
Sir, in topic oxygen requirement,
Okay.
uh, one term is also discussed, N naught minus N in TKN concentration.
Okay, okay. That is with respect to nitrification. So
Yes, sir.
whatever oxygen requirement that we are calculating basically is in terms of BOD, right? So that is the carbonaceous BOD we are talking about. So the initial part of the oxygen requirement is only about the carbonaceous BOD, but some part of oxygen is also being utilized for oxidizing the ammonia into nitrate. So ammonia, nitrate, all this we refer in terms of TKN, that is the total Geldal nitrogen. Okay. So we calculate the TKN and then 4.75, 4.57 is the coefficient. Like per gram of nitrate, this much oxygen is required. So it is a coefficient. So we have to subtract with it from the total CO2 requirement because that part is being utilized to oxidize the ammonia nitrogen into nitrate nitrogen. Okay. So we calculate the nitrate nitrogen in terms of TKN, organic nitrogen, everything in terms of TKN. So that's why it is 4.57. That is the coefficient into the TKN. Is it okay?
Sir, N naught and N are will be given in the question.
Yeah, yeah, yeah. Sure, surely, surely. L naught is the influent and Ne is the effluent. So both will definitely be given in the question.
Okay, sir.
If it is not given in the question, that means in that question they are not considering the nitrogenous BOD. They are not considering the oxidation of this ammonia. So that's why they have not given. But whenever you are designing a plant or designing an ASP in your later stage, then you should consider this also. But in most of the numerical problems that you will get in the textbooks or anywhere, you will not find this. But it is required for designing.
Otherwise, we will use only two terms.
Yeah, you will first Q into S naught minus AC, that term, total oxygen minus the oxygen required for the biomass growth.
Yes, sir.
Okay. Anything else?
Sir, in design criteria,
Okay.
if our theta c value is uh, comes out between 1025 and our HRT value is less than 12 or more than 24, so it means our calculation is not correct.
No, see, it depends on what type of system you are designing. Suppose you are designing a conventional plug flow type reactor, okay, then the theta c should be 5 to 8 days. Okay,
And
then
here our
yeah.
HRT is less than 4 or more than 6, so it means our calculation is wrong.
No, it doesn't mean that your calculation is wrong. It means that some of the parameters that you have chosen may be on the higher side. So suppose maybe you have to decrease your volume or increase your flow rate, something you have to do, and then you can get the HRT as per the suggested values. So there is nothing that what is right or wrong. We have to design in such a way that we will get sufficient time for biomass growth, for degradation of the organic matter. So these are the typical ranges. So if you follow all the procedure, all the mass balances and all the assumptions of ASP, you will definitely get these values. In case of conventional ASP and in case of extended aeration also, you will get values like very high HRT with respect to those things. So if you follow the assumptions, you will definitely get those values. And if you're not getting these values, that means you have to fine tune your other parameters. Maybe you have to increase the volume or decrease the flow rate, something you have to do. Okay. Our major aim is to grow the biomass sufficiently. Like suppose the MLVSS part in the case of the conventional should be in terms of 12,000 or 1,200 or something, 1,200 to 2,800, something like that. So you have to make sure that sufficient biomass has grown in the system for your degradation of organic matter. Rest all things will take care of itself. Okay. Hi Shrikar, you have joined the class very late. Actually, we are done with the session. So if you want to go through all the questions of this session, you can directly access my YouTube channel or the link provided by the NPTEL team. You will get all the questions and the solution part and also the video, recorded video. Okay. So still if you have any doubts, you can contact me over my email ID.
Okay, sir. Thank you.
Okay. Yeah. Please leave the session if you are done with it. Abdul Shrikar, do you have anything to ask? Hello, Abdul or Shrikar, do you have anything to ask?
No, no, sir.
Okay, then you can leave the session. Okay, please leave the session, Abdul.